It seems like a lot of the courses that we teach have a fundamental theorem. There's the fundamental theorem of calculus. There's the fundamental theorem of algebra. Well, we're at that point here in this class. We're going to talk about the central limit theorem. Central limit theorem is going to get a lot of work done for us. It's a really cool and amazing theorem that talks about, what happens when you sample and calculate statistics, calculate averages based on that sample. So let's start with a population. So we'll consider this a sample of size 1. Does this population look like it's normally distributed? No. Is it even close to normally distributed? No. But suppose you took some samples from this. Let's take a sample of size 10 and calculated the sample mean. Now from section 6.4 we know that the sample mean is going to have its own distribution. It's going to be perhaps different than the original population. And for samples of size 10, the sampling distribution would look like this. Is that a normal distribution? Does that look normal? No. It looks different, but it's certainly not normal. So what if we, instead of doing a sample of size 10, took a sample of size 20? Then the distribution of the sample means would look something like this. That's looking a little bit more familiar. Now remember what we started out as. We started out like this, with something that's very, very far from being a normal distribution. Samples of size 20, no, it's not looking too bad. Looks a little bit slanted to the right, but not too bad. And by the time you get to samples of size 30, regardless of the distribution you started out with, that distribution is starting to look pretty normal. That's amazing considering where we started out. We started out with this distribution, and if you take a modest sample of size 30, then all of a sudden the sample mean, x bar for samples of size 30, has a distribution which looks normal. That's pretty amazing. That regardless of where you start out, that at about a sample of size 30, the sample mean will have a normal or approximately normal distribution. So there's two cases that we're going to consider. Two cases under which, and I guess I didn't write it, under which x bar has a normal or approximately normal distribution. So let's go through these things. The first one is the one that I just talked about. So let's suppose x is a random variable and a sample from a population with a mean of mu and a standard deviation equal to sigma. For samples of size 30 or more, then the sample mean for whatever sample size is going to have an approximately normal distribution. The mean of that distribution is going to be the same as the mean of your original population. Original population had a mean of mu, so the mean of our normal distribution here is going to have that same mean. But the standard deviation is going to be different. The standard deviation in our new population is going to be smaller than it was for the old population. So that standard deviation is going to be sigma divided by the square root of n. Now this goes along with what we saw in section 6.4. Because as you increase the sample size, which is your n, then what's going to happen to this quotient overall? Your standard deviation. It's going to get smaller. It's going to decrease. And we saw that back in section 6.4, that as our sample size increased, the standard deviation decreased. The spread of the data decreased. So this is just confirming what we saw earlier. So that's one way that x bar is going to have a normal distribution. The other possibility is that x bar was a normally distributed random variable to begin with. So if x bar started out with a normal distribution, or if x started out with a normal distribution, that was its so-called parent population, then, you know, for any sample size, doesn't matter what the sample size is, that x bar is going to be distributed with that mean and the standard deviation. Basically the same thing as up above. You just don't have the requirement that n is greater than 30 anymore. This is true for any sample size. So down below here, I've got a couple different populations. Call it A, B, and C. So X is distributed normally with a mean of 100 and a standard deviation of 10. Which of these three curves do you think has to be this one as opposed to this one or this one? Let's do a little bit of math here, maybe help you out. If I have a sample of size 16, then from this population, the mean is still going to be 100, but the standard deviation is going to be 10 divided by 4, which is going to be 2.5. Or if I went all the way up to samples of size 100, then the mean is going to be 100 still. The standard deviation is going to be 10 divided by the square root of 100, which is 10. 10 over 10 is 1. So try and label for yourself which graph you think is which. Which graph is A, which graph is B, which graph is C. Then compare your graph, compare your answers with your neighbor. See if you guys are on the same page, and if you're not, then convince your neighbor that you're right. All right, so go ahead. This is your chance to interact with somebody other than Siri. So. All right, so let me remind you something you should keep in mind about this discussion. This is your mean, and this is your standard deviation. What does the standard deviation tell you about a population? How spread out the data is. Thank you. So the standard deviation here is 10, the standard deviation here is 2.5, standard deviation here is 1. Which curve does this have to be? Yeah, A is the shortest. Notice how wide this distribution is. It's a really wide distribution reflecting a lot of variability. So this is A, the next one's B, the next one's C. Now let's understand a little bit more about, sampling in larger and larger sample sizes. If you're drawing a sample, typically you actually don't know what the population is. So what you're hoping is that you get a good estimate of your population when you take your sample. Now, if you're sampling from this population, you draw a sample, are you likely to get something? And by this one, let me give that one some color. So in our orange population here, are you likely to get something really close to 100? Yeah, chances are you're not going to get something that's terribly close. So what you do is you say, all right, well, let's take a sample of size 16. And now you're dealing with this distribution. Now, when you sample from this, you can get any value, but are you likely to get something that's at least reasonably close to 100? Yeah, absolutely. And then last but not least, as you increase the sample size even more, all the way up to a size of 100, now what happens? I mean, can you really miss by much? If you're trying to estimate the population mean with samples of size 100, can you really miss by much? You can't. You're going to get something that's pretty close to that population mean. So large sample sizes are really desirable. There's only one problem with large sample sizes. It costs more money. So they're tough to get. It's a trade-off. Well, how accurate do you want to be? How much money do you want to spend? So those are questions that are going to go beyond this section, but they're things that people would have to address. So let's do a couple problems that relate to this. We'll start with problem number 6. Okay, so some of the problems on page 293 all relate back to this part right here. It says information about the overhead reach distance of adult females is that mu equals 205.5 centimeters with a standard deviation of 8.6 centimeters. And overhead reach distances are normally distributed based on data from the Federal Aviation Administration. So let's just copy this part down, that mu is 205.5 and sigma is 8.6. So I'm going to write it this way. X is distributed normally with a mean of 205.5 and a standard deviation of 8.6. Part A of problem 6 says, if one adult female is randomly selected, find the probability that her overhead reach is less than 196.9 centimeters. So what they're asking you for is a probability that X is less than 196.9 centimeters. Okay. Well, if you happen to have some of the graphing paper I gave you the other day, there's a good place for it. So we're sampling from this population. X is distributed normally with a mean of 205.5 and a standard deviation of 8.6. So this is 205.5. We want to find the probability that somebody has an overhead reach that's less than 196.9. So I'm just going to draw that about here, 196.9. Here's an important question for us. Which way should I be shading here, to the left or to the right? Good, to the left. I want to make sure that I get that area shaded correctly. So find my implements of math destruction. All right. So I want to shade to the left in this one. So that'd be this area. Well, we don't have this tabulated for just every normal curve. So what we'll do is we'll rewrite this and do this for the standard normal curve. We can calculate a z-value, which is counting how many z-scores away from the mean you are. 196.9 minus 205.5 divided by 8.6. What's that? Oh, is it negative 1? Oh, perfect. So negative 1 exactly? Yeah. Now that I look at it, yeah. Cool. So I want the area to the left of negative 1 on the z-tables. Should know that. It's like probably 34. Say again? 0.1587. All right, so 0.1587. So that's going to be this area here. So 0.1587 from our z-table. Thanks, Chris. Good, so there's part 6a. Now, a lot of these are going to have two parts. One of them is sampling from the original distribution. The other one is collecting a sample from that distribution. So this is the first part, but there's an important second part. Before I move on to that second part, are we okay with the first part? Let's try the second part. 6b. So part B says, if 36 adult females are randomly selected, find the probability that they have a mean overhead reach less than 205.5 centimeters. So the important difference here is that now we're talking about the distribution of the sample mean. What I want to highlight for you is that right here. That we're dealing with a sample of 36 adult females, and we want to find the probability that they have a mean overhead reach less than 205.0 centimeters. Okay, so for part B, what that means is we want to find the probability that x bar sub 36 is less than 205.0. Well, x was distributed normally with a mean of 205.5 and a standard deviation of 8.6. So here's where our central limit theorem comes in. X bar is going to have its own distribution. Now, because it comes from a normal distribution, x bar is also going to be normally distributed. What's the mean of this distribution going to equal? Thank you, 205.5. And the standard deviation is going to be 8.6 divided by what? Square root of 36. So this is the absolute key in the second part. You have to see that we need to apply the central limit theorem. So approximately 205.5 and 8.6 divided by 6. Thank you. 1.433, etc. So we're going to work with this distribution now. We want to find this probability based off of this distribution. So let's do that here. This time we have x bar for samples of size 36, which is distributed normally with a mean of 205.5 and a standard deviation of 1.433, etc. The rest of this calculation is going to be pretty much the same as it was in part 6a. We'll draw our distribution. Again, we have a mean of 205.5. We're looking for the probability that x is less than 205. So I'll squeeze that in here. 205. Do I want the area to the left or to the right? To the left. So let's stick to the left. We'll find that area by creating a z transformation, finding that area underneath the standard normal curve. So this is going to be z, which is distributed normally with a mean of 0 and a standard deviation of 1. (205 minus 205.5) divided by 1.433. All right, negative 0.3488. Now what you have to do is you have to be careful that you round this appropriately. In working with the z-tables, what digit do we need to round to? Hundredths. So this would be approximately negative 0.35. And Chris, I assume you're still ahead of me on this one, so go ahead. What's the area here? Good. From the z-table, 0.3632. So we're lucky in this one, again, that it's an area in the left tail because that's exactly what the z-tables give you. Let me just remind you of that calculation nonetheless. So the z-tables always give you the area in the left tail. So if you find z is negative 0.35, that's down here for the negative 0.3, and then across until you're underneath the 0.05. Chris was spot on at 0.3632. So certainly working with a sample of size 36 makes a difference to the distribution. And that's the big thing that I'm going to be testing is, are you using the correct distribution in finding these types of probabilities? So part of your points will be awarded for calculating the correct distribution, and then the rest will be awarded for finding the correct probability. How are we looking on problem number 6b? Yes? I'll provide you with the word problem. Yes. I'll probably also provide you with the graphs, and I'd most likely be really, really happy if you filled in the graphs. I think it helps you too in terms of calculating probabilities so that you know, gee, I don't need to subtract 1, or if I'm finding the area to the right, I do need to subtract from 1. It also gives you an estimate, gee, this probability should be less than a half, or if I had something that was, say, on the right side of the mean, then my probability should be more than 1/2, looking to the left, etc. So I'm hoping that it helps your critical thinking and helps you catch mistakes as you do this type of problem. So I will provide exactly the kinds of things you're seeing here. Thanks for the question. Anything else on problem 6 at all? Okay, so eventually my goal here is for you to try one yourself, but let's do one more together first. Problem number 12 was a little bit wordy and long, so let me do that one, and then I'll have you work on problem number 8. So problem number 12 and problem number 11 kind of go together. And problem number 12, you're looking at elevator safety. So elevators are typically given a 25% safety factor. That is, if you say that it can hold 2,500 pounds, really it can hold 25% more than that. So 25% more than that, 615 or 625, will give us an absolute limit of 3,125 pounds. If you're limiting yourself to 16 male passengers, then the average male passenger could have what is his weight? Well, let's see. 3,125 divided by 16. So that gives you about 195.3, as that's where this thing's going to break. So they asked, well, what's the probability that 16 male passengers have an average weight that's high enough that it would break here? Now they used in part A here the assumption that the mean weights are normally distributed with a mean of 182.9 and a standard deviation of 40.8. That is actually problem 11. But the safety recommendations were actually done with a smaller weight of 174 pounds instead of the more modern version, which is 182.9. So the question is, well, how would that affect the probability of overloading? Now you can calculate the probability in part 11 as part of your homework, but let's see what the effect is in problem number 12. So kind of a long-winded explanation here, but it boils down to this. Assuming that the mean weight of males is now 182.9 and not the value of 174 pounds that was used a few years ago, what do you conclude about the effect of using an outdated mean that is substantially lower than it should be? All right, so let's use this probability in calculating the probability of getting more people than 195.3, or excuse me, getting a value of 195.3 for the average weight of 16 males. All right, so problem number 12 here. We're going to assume that we have a population which is distributed with a mean of 174. So X is distributed with a mean of 174 and a standard deviation of 40.8. Boy, that's huge. You think about that. 40.8. Most data lies within how many standard deviations of the mean? 2. So if you do 2 standard deviations below that, this person's doesn't even weigh 100 pounds soaking wet. 2 standard deviations above, that's 250. That's somebody who should be in the NFL. That's a lot of variability in this data. That's a striking amount of variability. So if we sample from this distribution, samples of size 16, let's see if we can't figure out the distribution of the sample mean. So for samples of size 16, x bar sub 16 is going to be normally distributed with the same mean, 174. But what's going to happen to the standard deviation? What's the standard deviation for this new random variable of the sample mean? 40.8. Yeah, 40.8 divided by the square root of 16, which is 4. 40.8 divided by the square root of 16. So that's going to be 10.2. So that's the distribution that we're going to use in our calculation. So 174. In order for this elevator to be safe, we want to know what the probability is of finding a value out here in the tail of 195.3. That's kind of like the breaking point for this elevator. So what's the chances of exceeding that limit? So is that going to be the area in the right tail or the left tail? Right tail. So we want this probability here. Does that look like it's going to be a really big probability or a really small probability? Small. So keep that in mind as we look this up in our z tables. So the z-score is going to be 173 195.3 minus 174 divided by 10.2. Thank you. Rounded off, that's 2.06. So it's pretty far out in the right tail. Not much area there. So let's look up 2.06, even though I know Chris already has for me. 2.08? Uh-oh. Trouble in paradise. Let's take a look at this. Let's just double check things here. So, parentheses 195.3 minus 174 divided by 10.2. Okay. So yeah, if you round this to the nearest hundredth place, what should we look up? 2.09. All right, so 2.09. Hey, our elevator just got that much safer, right? All right, because you're farther out in the tail. 2.09 for our z value. 0.0183. Well, let's see here. When we look up 2.09, 2.0, and then all the way across to 0.09, we get 0.9817. But keep in mind what that represents. That 0.9817 is the area here to the left of that point. And that's not the area we want, is it? We want the area in the right tail. So how am I going to get the area in the right tail? Yeah, 1 minus that. 0.9817. Point what? 1183. 0183. Thank you. Yeah, 0183. So it looks like there's about a 1.83% chance of getting too many people in the elevator for its capacity. Which, 1.83% is not bad. But in comparison to problem 11, which uses a more up-to-date version of these weights, that probability increases to 11%, which that's not good. 11%, that's probably going to happen if you have enough people getting in often enough. So somebody has to revisit those standards. Okay, so what you should be getting out of this is this right here. When you're working with a distribution and you sample from that distribution, the sample mean has its own new distribution. In fact, here you go. Fill in the blank for me. The sample mean is a blank variable. Somebody said it. Random variable. It's going to have the same mean as your population, but the standard deviation is going to be sigma divided by the square root of n. So I'll be looking for this calculation, and then you can just find the z-scores and calculate your areas as usual, like we did in section 6.2 and section 6.3. Before I give you problem number 8, is there any other things that you'd like to discuss from problem number 12? Okay, so let me put up problem number 8, have you work on it. 2 parts to problem number 8. Keep in mind with problem number 8, you're again working with an overhead reach, which is normally distributed with a mean of 205.5 centimeters and a standard deviation of 8.6 centimeters. So the first part, you're sampling from that distribution. The second part, you're taking a mean of 25 females and looking at what happens to them on average.
206, right? Divided by 1.72. Like 2. Yep. Number 8, right? I'll leave it.
Make two mistakes that almost cancel each other out.
Yep.
Yeah, subtract some around, that'll give you a negative value on your left. No,
Sorry, it's just too much of a fix now. So leave it.
You got A, right? This is A. That's the answer to A.
Just read the wrong question, that's all.
25%.
Yep, that's A.
I read the wrong question. I got in between 0. But between the two, maybe. No, I'm not gonna fix it. I'll just leave it.
Okay.
It's fine.
This is where I wish I had a pause button for the videos. I don't. It just, you know, they tell me it would cost $800 to get the pause button installed for the software, and our IT department says no, can do, which is a bummer. All right, so let's take a look at this. Your calculations should look like this. Our original population had a mean of 205.5 and a standard deviation of 8.6. We want to find the probability that somebody has a reach that's greater than 195.0 centimeters. So that'd be the area to the right underneath this curve. We find that area by transforming this to a normal z-score. So if you wanted to, z is distributed normally with a mean of 0 and a standard deviation of 1. Looking up that area, negative 1.22 is going to give you the area to the left. So it's going to give you this little piece right here, the area in the left tail. So negative 1.22 turned out to be 0.1112. And the difference there is 0.8888. A bunch of 8s. So, we're okay with the first one? For the second one, the big thing, and this is where the majority of the points is going to be in an exam problem, is getting this second distribution correctly. You're going to take the same mean as your original population, but the standard deviation is going to be 8.6 divided by the square root of the sample size, giving you a 1.72. Our new z-score rounds to about negative 1.45. Negative 1.45. Go to the z table again. Negative 1.45. 0.0735. So again, that's going to be this area here in the left tail. 0.0735. And when we subtract, we'll get 0.9265. Yay. Okay, are you comfortable with these types of problems? You see what the central limit theorem is doing for us? Yes? Okay. Let me give you some homework, and then we'll take another break. So for homework, try problems 1 through 17. '17 is an interesting one. Talks about gondola safety in Vail, Colorado. So